All right, welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk, but if you have questions, you can unmute and ask questions. Or use chat room to post your questions so that we can address them in Q&A session. Second, today's DDPS seminar is open to external audience, so no classified discussion is allowed. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now let me briefly introduce our speaker today. It is an honor to host the Dimitris, who is the Jack Byrne, the professor in mathematics at Dartmouth College. He received bachelor's and master's degree in natural sciences from the University of Cambridge in 2001 and PhD degree in physics from the University of Chicago in 2009. Following a postdoctoral appointment at the Koopman Institute of Mathematical Science in New York University from 2009 to 2012, he was an assistant professor and associate professor of mathematics at Courant until 2021, when he joined the Department of Mathematics at Dartmouth. His current research focus is at the interface between operator-theoretic techniques for dynamical systems and machine learning. And his recent work includes the development of techniques for coherent pattern extractions, statistical forecasting, and data assimilation based on the data-driven approximations of Koopman operators of dynamical systems. He has worked on the applications of these tools to atmosphere, ocean science, fluid dynamics, and molecular dynamics. Today, the Dimitrios is going to talk about the quantum information and data science for modeling classical dynamics. Please expect a wonderful talk, and the stage is yours now, Dimitrios.
Thank you, Youngsu, Elon, for inviting me. Thank you, everyone, for coming in person or remotely. So we'll be talking about techniques for quantum information science and Koopman operator theory for modeling classical dynamical systems. This is in work done in collaboration with several people that I will acknowledge as we go through the talk. So this will allow me. Okay. So to begin, I usually like to show this snippet from a classical paper of Feynman, which in some ways ushered in the era of quantum computing, where the idea that he puts forward is that if nature is fundamentally quantum mechanical, we should be using quantum systems to simulate nature. In other words, quantum systems should be used to simulate other quantum systems, forming some notion of universal quantum computation. So now the problem I would like to talk about today is kind of in the converse direction. Namely, we would like to use quantum systems to simulate classical systems. And the idea being that we want to harness the power that quantum systems have that are not present in terms of information processing, that do not have classical analogs to obtain some type of computational advantage. So this is a problem that has also received a lot of attention in recent years. This is just a partial list of references where people have looked at different kinds of classical systems and designed quantum algorithms or thought about ways of incorporating quantum mechanical descriptions to simulate them. So one of the challenges here is that there's a little bit of a disparity between the fact that classical dynamical systems are usually formulated in terms of nonlinear systems of differential equations, either ordinary differential equations or partial differential equations, whereas quantum systems, if you exclude at least measurement, they evolve with unitary linear operations. So there is a immediate challenge about how to encode a nonlinear dynamics in terms of unitary or linear evolution. And there are also other complexities involved having to do with how you prepare the state of the quantum computer to encode given initial conditions of the classical system, and also at the end of the computation, how to appropriately measure the quantum state to extract the information that you want to predict the quantity of interest in the simulation. So these are all challenging and interesting questions, and I will be talking about work we've been doing with collaborators in, hoping to address at least part of them. Sorry, but okay. Okay, so I should say also that I'm happy to be interrupted at any time during the talk with questions, even if I don't get through the entire material. So we will be using, our methodology relies heavily on the operator-theoretic approaches to dynamical systems, which have been developed in work of von Neumann, Koopman, and others dating back to the 1930s. And in this framework, one focuses on the induced action of generally nonlinear dynamics on spaces of observables. So meaning functions of the state. These are quantities that one can measure, like a temperature or velocity in fluid flow. And the idea here is that these spaces, spaces of functions, if the codomain, so the output space, is a linear space, like a vector space, oftentimes this will be the real or complex numbers, these spaces are actually linear, meaning we can add together functions, we can scalar multiply functions, even if the underlying state space of the classical system does not have linear structure. And remarkably, if we have a generally nonlinear flow, I'm denoting it here by phi t on a classical state space, and by that I mean that there is this family of mappings parameterized by time, such that they take in initial conditions on the state space X and output the state that the system has reached after dynamical evolution for time t. And this is generally a nonlinear. Yes?
Excuse me, I'm sorry, I'm Henry. So before you go further, can you maybe give a few example of in a physical system, what is X, what is phi t, what is Y?
Thanks for the question. So maybe to have as a mental model, a concrete example, suppose that X is three-dimensional space or some Euclidean space, Rn, and we have on X, we have specified a system of n ordinary differential equations. Think of, for instance, the Lorentz 63, a system that has the chaotic butterfly attractor, or think of the simple harmonic oscillator if X was R2, where you have position and momentum represented in that space. So you write down a system of equations, dx by dt equals v of x, where v is some vector field, and you solve the initial value problem that comes out of that, and the solution defines this dynamical flow, phi t. This is the map that basically is the solution map for a system of differential equations. And these can also be generalized to systems of partial differential equations, where now X, instead of being a finite dimensional space like Rn, it's actually itself a function space. If you're dealing with a fluid mechanical model, so X would be a space of functions on some domain where the fluid flow takes place. Does that help clarify?
Yeah. Thanks.
Yeah. And again, please interrupt me if anything is not clear. So now, given that we have such a flow, we can define linear operators associated with that flow. that they act by composition. So a natural such operator, which is now known the Koopman operator, takes observables, so functions in this space, are suitably chosen, and composes them from the right with a dynamical flow. So this effectively defines a transformation that takes functions and produces new functions. You can think of the function f composed with phi t as some type of time-evolved version of f, where instead of evaluating f at any given classical state, we're evaluating it at, since we're composing with this map, we're evaluating at the state that the system has reached after evolution by time t. And you can check that this transformation is actually linear, that the way we define this map from functions to functions is actually a linear map. This is now known as the Koopman operator. A related operator that is also quite useful is the transfer operator, or also known as Perron-Frobenius operator. And this is actually like an adjoint. You can think of it as an adjoint of the Koopman operator, which is defined on a dual space to f. I don't want to go into the technical details here, but we're thinking that, for instance, if f was a space of continuous functions on x, then the dual space would be some space of measures, like for instance probability measures. And the Perron-Frobenius operator describes the action of a dynamical system on spaces of measures. And this is useful in studying probabilistic aspects of classical dynamics, namely how probability distributions evolve under general, nonlinear dynamics. This has applications in forecasting, uncertainty quantification, and so on. But the main message here is that this perspective allows one basically to study general, nonlinear dynamics by leveraging tools from the theory of linear operators. This is something that has received, this approach has received a fair amount of attention in recent years, because these linear operator theoretic techniques are also well suited for data-driven implementation, it turns out, or data-driven approximation, where we use observations of the system collected along dynamical trajectories to build approximations of the Koopman or transfer operator and use them for different purposes. The primary applications being spectral decomposition of data. It turns out that these operators, when formulated in on appropriately chosen spaces, they have useful spectral properties. So for instance, their eigenfunctions they can characterize periodic or approximately periodic observables under the flow. And this can be used for sort of pattern extraction or feature extraction from dynamically generated data. And the other application is prediction or modeling and uncertainty quantification. Now, for the purposes of this talk here, what I will be focusing rather are on the connections between this approach, this general framework of Koopman and transfer operators, with quantum theory. So mathematically, it turns out that there are some deep correspondences and relationships between the two fields, which I hope I will highlight, and also kind of like motivate this framework as a way to build a bridge to effectively encode classical dynamics in terms of quantum systems. So this is like a natural language in some sense to do that. Okay, so this maybe here, maybe for this audience, this is not strictly necessary, but I have like a one-slide summary of the basic axioms of quantum mechanics, which we will be using later on. And in many ways, you can think of a quantum set of quantum mechanical axioms as being analogous to classical statistics, where you replace objects like probability densities, which are functions, and observables, which are again functions, by operators. So it's some type of, you can think of it, operator-theoretic or non-commutative version of classical probability. And one of the fundamental notions that we have is that of a density operator. So basically a quantum state, we're going to describe it by an operator that acts on a Hilbert space. And that choice of Hilbert space will depend on the system at hand. For something like the hydrogen atom, it would be like a space of functions over three-dimensional space. For a spin system, it could be like a finite dimensional Hilbert space. This will depend on the system that we have at hand. But a density operator is an operator that has that is positive, meaning it's self-adjoint and its spectrum lies in the positive real line. It is of trace class, so it has finite trace, and it's normalized in the sense that its trace is equal to 1. And you can think of it as somehow being analogous to a probability density function that one has in classical statistics, in the sense that a probability density function is a positive function. It is integrable, and its integral is equal to 1. So thinking here of trace as being somewhat analogous to integration makes that correspondence. Now, observables in quantum mechanics are, again, operators. In fact, they are self-adjoint operators acting on the Hilbert space. Here, for simplicity, I'm going to think in terms of bounded observables. That doesn't necessarily have to be the case, but we don't have to worry about that now. And the self-adjointness here, you can think of it as being analogous to having real-valued functions, classical observables. So self-adjoint operators have real spectra, which is analogous to having to being real-valued functions. Now, the quantum theory gives us a recipe, or like a set of rules for computing expectations of measurements of observables, given that the system is in a certain quantum state, and evaluating their probability outcomes. And again, this generalized familiar notions from classical statistics. So if we have a system that is in quantum state rho, it has an associated density operator rho, and we have a bounded classical, bounded quantum observable, we can compute this trace, and that gives us a number, which is we interpret as the expected value of measurements of A when the system is in quantum state rho. And again, thinking of trace as being analogous to integration, rho as being analogous to a probability density, and A as being analogous to a classical observable, this formula here should look somewhat familiar from somewhat analogous to expectation of classical in classical statistics. Now, quantum theory also gives us a recipe for computing the probability of outcomes of measurements. So if we have a set omega that is like some set of interest, let's say an interval, and we want to compute the probability that a measurement of A will lie on that interval, we can compute that again as a quantum expectation of a new quantum observable, which is basically the spectral measure associated with A. I don't want to go now in more details here, but think of this as being somewhat analogous to when you want to compute the probability of an event in classical statistics. You can write the probability of an event as an expectation value of a characteristic function that basically indexes, represents that event. Here, this spectral measure is some quantum version of a characteristic function. It's a projection operator that we can use to compute probabilities of measurement. Now, the evolution of a quantum state takes place under unitary dynamics when we are not measuring the system. So we assume that there is a unitary operator, UT, that acts on densities, maps quantum density operators to quantum density operators by means of this conjugation identity. In quantum physics, this is known as the Schrödinger picture of quantum evolution. And it's linear. That's meaning these operators here are linear. And the last piece that I want to bring up here is that just as in classical statistics, we can condition probability densities by when we have observed events using Bayes rule. There is an analogous conditioning procedure for conditioning quantum states by so-called quantum events. So what are quantum events? So quantum events are, again, operators. Everything is an operator here, which have the property of being positive and lying between the zero operator and the identity operator. These are also known as quantum effects. And again, you can think of this in a sort of classical analogy with the fact that when you have an event that you're conditioning a probability density, that event you can represent by a characteristic function. And a characteristic function is a function that takes values between the zero function and the function that is equal to 1 everywhere. And this generalizes that. Now, this formula here, you will see that we have this square root that appears on both sides of the density operator, which looks somewhat different from the classical version of Bayes rule when you write it down. Well, the reason is that we're dealing with these non-commutative spaces of operators. If we were able to commute multiplication of the square root of E with rho, we could write this as rho times E, which would then look closer to what a conditioning in the classical world would look like. But because we're not in general allowed to do this, this is the formula that we're going to be using. Okay, so we have now this set of axioms. Maybe I should pause quickly to ask if there are any questions. So what we want to do is
yes. I do have a question. I'm sorry. So, like, can you? I'm a little unfamiliar with, like, coming from a physics background. I'm familiar with like point 1 to 4. Can you say a little more about the 5th point, state conditioning by measurement? Like, what is it? What are you measuring?
Yeah. It's so here I'm thinking of for every measurement there's one can assign by measurement here I mean these quantum events or effects. So if you want to think of it purely as without focusing so much on the choice of words here, and then I can try to clarify that. Think of that whenever you have an operator E that has this property, it has this. It's called a quantum effect. Then there is this formula that is basically giving you a quantum version of Bayes rule. Now, when you're actually making a measurement, and if we want to think at least of the measurement as a type of a yes or no answer, or yes or no question, it turns out that you can write down an effect. You can write down an E for depends on whether you got the answer yes or the answer no, and you can condition the state by this effect. This is basically analogous to what one might call the wave function quotes collapse. I don't know if I want to really use that word, but this is basically somewhat analogous to that. I mean, for us, we're going to think of it more in a statistical sense, or we're going to use it in a mathematical sense to update quantum states by outcomes of observations of our system. Hopefully, this will become a little bit clearer later on. But
so I mean, can you say like this is what happens after you make a measurement?
Yes, you can say that. Yeah. But also but also you can use that formula not just in the context of a physical quantum measurement, like in terms of like a hardware based measurement, but you can also think of it as an inference formula, similarly to how you would treat, Bayesian, Bayes rule for inference.
So one of terms is kind of projection, yeah, some subspace.
This map here,
yeah.
Projections will have that property. There will be quantum effects, but not every quantum effect is necessarily a projection. But yeah, that's a good point. Like projections are going to be part of this. Okay. All right. So now I want to go over like a big picture overview of how we use these axioms to represent a classical dynamical system by a quantum system. So as we mentioned earlier, we're starting from a classical dynamical flow on a state space, and we want to embed this classical flow eventually to a quantum system. And we're going to do this by passing through a few intermediate levels. The first one of which will be to embed a classical evolution of classical states into evolution of classical probability distributions. The way to do that, so here P of X denotes a space of probability measures over X. With reasonable assumptions, this is like a nice space in a mathematical sense, and the map that allows us to do that is it's very natural. It takes points in X and maps them to their corresponding Dirac delta measures at that point. So essentially, what we're doing here, we're creating a copy of our system into this space of probability measures that we can always do. I mean, there are more, of course, probability measures in here than just the Dirac measures, but we get an injective mapping, like a one-to-one mapping into the space P of X. And on this space P of X, we can use this Perron-Frobenius operator that I introduced earlier on, which is this, it's a composition map by the inverse flow, it turns out, to evolve probability measures over time. And the important thing about this type of embedding is that it's dynamically consistent in the sense that this diagram here commutes. By that, I mean that if you start from a given classical initial condition, you embed it into a probability measure, sending it to its corresponding Dirac, evolving it under the transfer operator, you get to the same point as first evolving your classical condition and then embedding it with the same formula. So it's dynamically consistent in that manner. Now, what we want to do next is starting from this level of description, so to speak, we want to now create another embedding, which takes classical probability measures into quantum states. So here H is a Hilbert space that we will have to choose. We'll have to think about how to define it. And Q of H denotes the space of quantum states on that Hilbert space. So for us, this will be the set of trace class positive operators of unit trace. We want to define a mapping that will be an embedding that I'm calling here gamma, that takes classical probability measures and creates from them quantum states. And we also want to prescribe an evolution map that acts on this quantum states. This will be some kind of like a lifted version of the Perron-Frobenius operator that makes this diagram commute. So in effect, this will give us this will give us a copy of our system into a quantum mechanical system. Now, this system is going to be typically infinite dimensional. In order to have, of course, practical algorithms, we want to project into finite dimensions. And in particular, we want if the goal is to create quantum computational algorithms, we want to project our system into a quantum system that is defined on a Hilbert space, which is associated with a certain number of qubits. So it has B sub n here, I'm denoting as a tensor product Hilbert space associated with n qubits. The goal is we want to define a choose our projection map in a suitable way such that we can have a evolution acting at the level of qubits that is in some sense, on the one hand, efficient, that allows, which means that we can implement it with a modest number of quantum logic gates, and also it's consistent in the sense that this diagram here should commute, or at least commute asymptotically as the number of qubits increases. And that is kind of the end goal. Now, the key points that I want, probably I will not get to the very end of everything that I wanted to say, but so let me say what are the key points here. There are 2 points that I want to highlight. The first is that even if we implement these methods classically, like after all, these are basically, one could, in principle, simulate this system classically at the level of operators. It's basically dealing with linear algebra when you're working in finite dimensions. What I'd like to one of the messages I'd like to get across is that even if implemented classically, working with this quantum formalism has certain desirable or useful numerical properties, certain aspects of structure preservation that are very natural or almost automatic when you're working with operators or like matrices in finite dimensions, as opposed to functions. I will focus here on positivity preservation. And the other aspect is that for some classes of systems, which is by no means an exhaustive class, I will specify that later on, we do have a way to design circuits that implement this evolution in a manner that is efficient, or it has some type of advantage. And I will try to be specific about what is that advantage later on. But these are the main 2 points. So I'm going to highlight, give some examples from our work. First, we're dealing more with this part where we design algorithms which are quantum inspired, but they're implemented classically. And then on the second part, talk about implementations on quantum circuits. So this first part is in work in collaboration with David Freeman, Brian Meads, who are PhD students from Dartmouth, Joanna Slawinska, who is also from Dartmouth, and Abbas Urmas from University of Wisconsin, Milwaukee. And I will be talking about ideas from using quantum information science or quantum theory to perform data simulations of classical dynamical systems. So what is the goal here in data simulation? Well, the goal is that you have the objective rather is that we have a dynamical system that we observe only partially in a classical dynamical system, and we have classical observations, and we want to infer the state of that system under sequential measurement. So the idea is that we could start from a highly uncertain knowledge of the state, and even though we're observing the system partially, over time we can refine our knowledge and get a good estimate of the underlying state. So this is an integral piece of many sort of like numerical modeling systems like weather prediction or object tracking, and it has many applications in practice. So the approach that we're going to use is basically along the lines of what I've been describing already. What I'm going to be here a little bit more specific in how we actually define our Hilbert spaces and our spaces of classical observables, which I hadn't talked about previously. First, if we're going to embed into a quantum system, we have to choose a Hilbert space. So in the context of data assimilation, a natural choice of a Hilbert space is if you have a dynamical system that is measure preserving. So this is going to be an assumption. We're going to assume that there is a invariant probability distribution of the system. Think of it that there is some kind of statistical equilibrium. The system itself, like the probabilities that we're going to be looking at, they do not have to be in equilibrium, but we're thinking that there is some underlying equilibrium distribution, and the probability measures that we're looking at, they have densities with respect to that equilibrium distribution. So this is the typical setup one has in classical data assimilation. And now, as our space of observables, we're going to look at bounded functions with respect to that probability measure. Now, we can think of this space, this space of observables, as it is actually an algebra of observables. What do I mean by that? It has the property of not just being a vector space, like a linear space where you have addition and scalar multiplication, but it has an extra operation, namely you can multiply together two functions in this space, and they stay in that space, and the operation is continuous in a suitable sense with respect to the norm of the space. So we have an algebra, and it is a commutative algebra because it doesn't matter in which order you multiply functions. Later on, we're going to embed this in a non-commutative algebra of operators. So in fact, this is what we're going to do now. This is how we embed our classical probability densities into quantum states. So it's basically a formula that takes a probability measure that has a density with respect to the invariant measure mu, and call that density, I'm calling it nu. This is a function which is integrable because it's a probability density. So it is positive, so we can take its square root, and its square root is going to be square integrable, so it will live in our Hilbert space. And if we define that operator, which is a projection operator that projects along the square root of the probability density, that defines for us a quantum state. This is a density operator. So this procedure is known as the Koopman von Neumann embedding. Elon and others have done a lot of work on this topic, or even more general versions of this, where you allow also the density here to have a complex phase. Here we're looking at real valued densities. And so we have this embedding, and the nice thing about it is that it makes this diagram commute, where the commutation here, the evolution of quantum state, takes by means of the Koopman operator acting on probability on density operators by this conjugation formula we had talked about earlier. Now, so we've talked about how to embed classical states. Now we can also embed classical observables. After all, we want to have both representation of states and observables as a quantum system. And the way we can do that is basically by mapping functions to bounded operators on our Hilbert space. So this will be quantum observables, which are multiplication operators that multiply by those functions. So here pi is a map that takes a function to an operator. So pi of f is an operator, and pi of f is defined as the operator that multiplies by f. So in quantum mechanics, there are, in quantum physics, multiplication operators. There are many examples of them, one of them being, let's say, the position operator in a one-dimensional system. Here we're defining them for general observables in this space L infinity. It is important that we're looking at bounded observables because to make this operator bounded, this multiplication operator. And the consistency relation that we get at the end, so this is why this diagram commute, and this is why effectively we're creating a copy of our system into a quantum system, is that we can compute, we can use the transfer operator to evolve classical probability densities and compute expectations, classical expectations, with that with respect to that time evolved density, or we can embed quantum mechanically, use the quantum mechanical version of the transfer operator and compute a quantum expectation of the corresponding multiplication operator pi of f. So basically it's this formula over here, and we get the same result as the classical expectation. In other words, we have created a copy for all intents and purposes of our system into this infinite dimensional quantum system. Now, we want this, of course, at the end of the day, we want to do numerical computation. So the next step will be actually to, as I mentioned earlier as well, will be to project the system onto finite dimensions. Now, here I'm not focusing on doing quantum computing, so it's not important that the Hilbert space, the finite dimensional Hilbert space is has the tensor product structure associated with qubits. Here we're imagining a more general situation where we have some finite dimensional Hilbert space, which is a subspace of H, of our infinite dimensional Hilbert space, and we orthogonally project everything onto that subspace. Now we can project states, assuming that this denominator here doesn't vanish. So for every state for which this denominator doesn't vanish, we can project down a state from the infinite dimensional setting to a finite dimensional state. And we can also create an evolution of states by means of this this formula here, which is where we're basically using a projected quantum projected Koopman operator for that part. Now, in general, if we do that, this diagram here does not commute. That's why I put here these dotted arrows, unless, in some special cases, for instance, if H sub L was a finite union of Koopman eigenspaces, then, for particular choices of H sub L, this diagram will commute exactly, but we don't want to restrict ourselves in that situation. However, if we have L as being some parameter that controls the dimension of our approximation, and as L increases, these spaces increase towards H, this diagram here will commute in an asymptotic sense. So this is the level that we operate numerically. We have basically our quantum states are density matrices now. They are finite rank operators and numerical linear algebra with matrix algebra. And this is now one of these highlights that I wanted to make earlier, is that this numerical setup allows us to easily preserve some structures of the problem that in ways that would not be possible by if we were working in spaces of functions. And what do I mean by that? Well, if you take a classical probability density, like a function, which is positive, if you do an orthogonal projection of a positive function, let's say you were representing in a numerical scheme a classical density as in a basis, like in a Fourier basis or some type of discretization basis that one chooses. If you're using an orthogonal projection to arrive at your approximation, that approximation need not be positive. And there are things, behaviors like the Gibbs phenomenon, for instance, when you take a top hat function and you project it into finitely many Fourier functions, which do not preserve positivity, at least not through orthogonal projections. You have to do something less trivial in order to preserve positivity. On the other hand, preserving positivity of operators is comparatively much easier. If you take an operator and you conjugate it from the left and right by a positive operator, and you conjugate it by projections, the result is a positive operator. So the message here is that by embedding first our system into this infinite dimensional quantum system and using that as our starting point to build numerical approximations, puts us in a space where we have the ability to preserve certain aspects of the original system, like positivity of states, but also, it turns out, positivity of observables, in ways that are not possible in spaces of functions using equivalent operations like orthogonal, analogous operations like orthogonal projections. So I would advocate that this is a reason to at least think about these type of methodologies, even if they're not implemented in quantum computers, even if they're used in classical numerics. Okay, so in data simulation, as I mentioned earlier, we imagine that we have a classical system that is evolving over time. We don't have knowledge of its state, but we observe its state every certain number of time steps if we're doing some kind of discrete in time approximation. And we're going to represent our knowledge of that system by a quantum state. So in data simulation, classical data simulation, this knowledge would be represented by a probability density. Here we're going to use a density matrix like we had before. And the idea is that we alternate between forecast and measurement. This is the typical cycle one has in data assimilation. Between observations, we use the transfer operator acting on the density matrices to evolve our density to a new density. And then when we make a measurement of the system, and by measurement here I mean purely in the classical sense, we have a sensor or a network of sensors that are giving us observations, and we're measuring a function of the state of our classical system. We use the quantum version of Bayes' rule that I showed earlier to update the state. And for that, we have to use basically a map, like as I was talking about earlier. We have to assign to every observation a corresponding quantum effect. So like a quantum event, if you want to think of it like that way. We do that in practice using kernel methods, like feature maps from reproducing kernel Hilbert spaces, with the difference that being in the quantum world, we have to use a matrix valued or operator valued feature maps. I'm happy to talk about some of this offline later on. So, and the scheme it's basically numerically we can implement it using data that we collect along dynamical trajectories in a training phase. So it's basically like a data-driven data simulation scheme. So I guess I talked through that. So in the interest of time, I will not spend too much time here, but I want to emphasize that we can compute predictions or forecasts of classical observables using quantum expectations, but we can also we're basically carrying we're representing entire forecast distributions because with our quantum state and the spectral resolution of our observables, we can compute probabilities for measurements to take values in different sets of interest. Let's say you want to predict that the temperature at a given location, 2 days from today will lie in a certain interval. This can be encoded in this manner. Okay, I'm going to show one example where we did that in the context of climate dynamics. So This is using data that as training that was generated from a climate model. So currently we're working also on doing this from actual observational data. But the idea is that we're making observations of the Indo-Pacific sea surface temperature fields. So we're observing the temperature of the surface temperature of the ocean in a domain that is roughly like shown here. And from that, we want to make a prediction about the El Nino phenomenon. So the El Nino Southern Oscillation is an oscillatory process that manifests itself with anomalously warm or anomalously cold waters in the tropical Pacific Ocean to the west of South America. So El Nino events are anomalously warm, and the corresponding La Niñas are anomalously cold. This is an oscillation that takes place with a characteristic time scale of 3 to 7 years approximately. Currently, we are in an El Nino year. And the way climate scientists index or monitor this phenomenon is by means of, conventionally at least, by means of so-called Nino indices. So these are basically area averaged sea surface temperature fields over given domains in the tropical Pacific Ocean. We're going to use this Nino 3.4 index, which is the average SST in this box over here, which is probably one of the more common indices for ENSO. So we took this data and we ran it through the pipeline that I just mentioned, and this is basically just an output of what this method produces. So these are basically running forecasts of the El Nino 3.4 index in a I think 50 or so, or 20 years of an arbitrary interval of a test data set that we had isolated from this model. And in the red line, we're showing the true evolution of the Nino 3.4 index. The black line is showing the evolution that the quantum that we get from the quantum expectation from this numerical scheme. Here in the horizontal axis, we have the forecast verification time. So it's like the day for which we are making the forecast. And as we go down the panel, we are increasing the lead time. It's how many days in advance we are predicting. And the behavior here that you can see, well, I should also say that the colors here correspond to the probability or logarithms of the probability density that, again, is encoded in our quantum state, computed through the spectral measure of our observable that we're using to also characterize uncertainty of forecasting. And you can see as we go down the panels, as one might expect, forecast uncertainty increases as well as the error for the forecast, but it is doing a pretty decent job, at least for this type of modeled data. Okay, so I think I'm almost running out of time, so I will skip basically a lot of what I had in mind. I will say maybe just a few words about the actual quantum implementation. If I can take 3 to
yeah.
So in this part, and I'm just going to give a quick summary of this. We are now interested in besides this numerical classical numerical procedure that I outlined for data assimilation. Now we're interested in actually implementing this the versions of this algorithms onto quantum computers. So this is work done with people listed here, and the focus here is that rather than having our finite dimensional approximation space be a general finite dimensional Hilbert space, we want to explicitly focus in the case where the Hilbert space that we are projecting has the structure of an n-fold tensor product of 2-dimensional Hilbert spaces associated with n n qubits of a quantum computer. So this space here will have dimension 2 to the power n, and there is basically a canonical basis that one can choose for this tensor product Hilbert space that you can represent by binary strings, indexed by binary strings of length n, and the basis vectors are tensor products of these basic vectors that are we label them with this Dirac ket notation, either 0 and 1. So we have this setup here, and this space here has dimension 2 to the power n, so an exponentially large dimension. We want to create here. The goal is to create an evolution, find a projection map such that it maps our transfer operator into a finite dimensional, a finite rank operator that can be implemented efficiently using ideally using a polynomial number of quantum gates in this exponentially large dimensional Hilbert space. So this is something that we're actively working on so far, and we've had a lot of discussions with Elon and others on that as well. So far we have looked at this particular case of so-called systems that have pure point spectrum. So these are canonically, we can represent them as ergodic rotations on tori. So this is a formula that I'm showing here for the dynamical evolution. This will be our canonical working example, but in fact, this is representative of a wider class of systems, so we can bring other systems that have this pure point spectrum property into this canonical form of an ergodic torus rotation by continuous transformations that are compatible with the dynamics. These are known as topological conjugacies. So this will be our canonical example that we're going to study. I'm going to skip here through a few things, but the idea is that we want to choose a Hilbert space that is adapted to this kind of type of systems, and we're not going to be using an L2 space in this application. We're going to use a different class of Hilbert space known as a reproducing kernel Hilbert space. So it's defined by means of a kernel that we have on our torus. And the key property that this space it has, in addition to being a reproducing kernel Hilbert space, that it's also again an algebra with respect to pointwise multiplication of functions. This is a non-trivial property to have for a reproducing kernel Hilbert space, but for this specific choice of kernel that we're using, we have it. And the reason is that we want to have these properties because we want to represent classical observables of functions in that Hilbert space by bounded multiplication operators. And this type of this class of spaces have been studied extensively in harmonic analysis by Fachtinger and collaborators, and among there's a large literature, and we've made some contributions in that as well. I'm going to skip a bunch of stuff. The point being that with this particular choice of spaces, we're calling them reproducing kernel Hilbert algebras, we're able to retain a lot of structure that is you can find in different spaces, but here we're putting them all in one setup, and this is useful for designing our quantum algorithms. Okay, so the main point is that once we go through this machinery, is that if we take a system that has pure point spectrum and we look at its, we can find basically a projection map that takes our Koopman operator, or more precisely the generator of the Koopman group, to a Hamiltonian. So we're using a Hamiltonian to define a quantum system that is very nicely factorizable in terms of as a sum of commuting operators, which are very simple in the sense that each of these operators that appears in the sum is a tensor product of identity operators with only one Pauli Z operator that acts on an individual qubit. So effectively what we're doing, we're representing this ergodic system that has pure point spectrum as a bunch of phase rotations that are acting on individual qubits. This is very special in the because it won't work for any dynamical system. I want to stress that. It's actually non-trivial to generalize it, but for this kind of systems, we do have an efficient representation of our quantum Hamiltonian that allows us to exponentiate it and get a very nice, very simple, almost trivially simple quantum circuit. This is how the pipeline works. As I mentioned earlier, in addition to the evolution, which we do efficiently by our the circuit that I just highlighted, or the highlighted, there are these problems of how do you encode the initial condition and how do you make a measurement at the end where which gives you a consistent information about the observable that you want to predict. There are ways to address it. I'm not talking about this today. Namely, the state preparation can be done efficiently using Hadamard gates, and at the end of the Koopman evolution, it turns out by applying a quantum Fourier transform, which is also an efficient in the sense of being it has a quadratic cost, and it requires circuits of quadratic depth in the number of qubits. After doing this quantum Fourier transform, it turns out that measurement in the quantum computer can be decoded into a measurement of the classical observable that one is interested in predicting. And this scheme has this positivity preservation property that we talked about earlier. It is asymptotically consistent as the number of qubits increases, and it has an advantage in this very specific sense. I don't want to, definitely not want to overclaim here, in the sense that it can simulate spaces of observables which are exponentially large using circuits that have quadratic depth. So the running time of the algorithm is quadratic in the number of qubits, and that allows you to simulate the evolution of observables in an exponentially large dimensional Hilbert space. So I'm just showing here one or two examples where we have applied that into simple systems like harmonic oscillators or quasi-periodic systems that live on a torus. So to have a more interesting, this is evolution. This is comparing the true evolution with the ensemble mean that one obtains from a collection of quantum measurements done at the end, from an ensemble of identically prepared quantum systems that this is done in a simulated quantum circuit experiment. So you can see that with a certain number of qubits, we can get a reasonable reconstruction of the true evolution. And that would be the last point. We also had some actual experiments done on a IBM quantum computer using 3 qubits. So this is admittedly for a very simple system, just a harmonic oscillator. Where beyond that, we found that basically the noise in the quantum computer prevented us from getting any meaningful result. But I think this is encouraging because at least we get a consistent, this is like an ideal quantum circuit versus the actual one. Albeit for this system, a simple system, we can get a consistent, a reasonably consistent correspondent. Okay, so with that, I will stop and I'll just leave this here, and I'm sorry for taking a little bit longer.
Well, thank you so much. That was a wonderful talk. And let's have a Q&A session, although we had a question in the middle during the talk. Is there anyone who wants to ask questions? Please unmute yourself and ask. And for those of you who are in person in that room physically, please ask questions as well if you have one. Well, I can start with one. When you show the chart like showing the classical, the dynamics, and there's a mapping from classical to quantum and quantum to computation, quantum computational. There's a map you have to define, right? And is that map has to be linear in with respect to the input space?
No, actually it's, yeah, and that's one of the few places where the mappings are not linear. Like if we look at, sorry, just go back real quick. If you look at this map here, this is this Koopman von Neumann embedding. This is actually a nonlinear map because it involves basically, we're doing operations like square roots. So this is actually, these mappings are one of the few places where this scheme is nonlinear. I mean, the other place is the measurement when we do the quantum state update. But yeah, in general, these mappings here are not linear.
Yeah, it's just fascinating to me. I mean, me being not familiar with this subject, how people identify those nonlinear map. There must be some rules.
Well, I don't know if I can say something too intelligent. Maybe Elon will have some comments on that. But like, if I were to have a shot, is like there are maybe some at least some guidelines. Like you want, like for instance, you might say, okay, we want to have our classical probability density if we're going to look for a so-called vector state. Vector state, it means that it's a density operator that you can characterize by a specific wave function. So it's like a single function that characterizes like a rank 1 projection operator. So we have to basically identify like a function that is a unit vector, since this is a projection operator, from the data that we were given, namely that probability density. And since a probability density is a positive function that integrates to 1, if I want to turn it into a unit vector on a Hilbert space, which is contains square integrable functions, well, maybe the square root is not a bad idea. And here's the formula.
Yeah.
I don't know if there's a more principled way of thinking about this.
Yeah.
I mean, there's also nonlinearity in the sense in the choice of like how you like what coordinates say you would choose on the space, or like, right, like how, like, because H and X are very different objects, and gamma like gives you an enormous amount of freedom in how you make that identification. But like, and maybe you want, if the dynamics has based on symmetries, so you want to like encode that with a proper choice of coordinates on X, then the symmetries need to have a special representation on H, having to do with how that gamma map is acting. But in general, in general, I think, construction of these maps is kind of like sort of cutting edge research topic. And I think Dimitri and his colleagues have done amazing work, in terms of pushing the envelope here.
Got it. Well, from the perspective of reduced to the model guy, I'm one of them, and this operator mapping, that's we do all the times. In the context of we generally, the reason we are doing that operator mapping, because the dynamics is in really high dimensional space, and you want to reduce that to low dimensional space, and that mapping, like typically we call it compression. There are linear map and nonlinear map, and we do that all the times to bring those high dimensional space to the low dimensional space. And as you guys mentioned, if there's some physical property we would like to preserve, we follow that rule. Those physical property to guide us to come up with those mapping, like from high dimensional to low dimensional. Yeah, so there is some connection between ROM and, I mean, one definite, clear example is DMD. DMD is a one Koopman operator, and it does the linear compression, like the SVD type of mapping from high dimensional to low dimensional.
One thing I should note is that this is at least this map, right? This is kind of like the opposite of a compression. Is like an extreme sort of dimension augmentation. Yeah, it's a lift. Yeah, because you start from a space which it's in some sense much smaller than this space. We're creating a copy of probability measures into quantum states.
Yeah,
I mean, what the compression happens when we go from here and then we go to this level of density matrices, and that is a compression. Like
there's a concept called the lift and something, and where there's the original governing equation is very complex nonlinear, but you do the augmentations, basically lifting what you just said, and in order to transform that complex nonlinear problems to the quadratic problems. And then once you convert that to quadratic, it's easy to deal, reduce further to low dimensional space. So there's the work by the German people and also Karen Wilcox in UT Austin. Are you familiar with that?
Lift and learn.
Yeah, exactly. Yeah.
It's in kind of a similar. Yeah, I think that's a common strategy, like that. You going to bigger spaces gives you maybe more flexibility than to design approximation schemes that have some properties that you couldn't easily get otherwise.
And you guys, that's what you're doing, right? Basically.
At least in this example, yeah, because here there's nothing specific to quantum computing. I mean, this you could just think of it purely as a numerical data-driven scheme for data assimilation. It gives you this type of benefit. And again, I'm not arguing that there are no other ways. Of course, there are different ways of enforcing positivity, approximations. But the thing that I was trying to argue is that certain operations that are non-trivial in a function world, like for instance, how do you make sure that you preserve positivity of positive functions? They become somehow almost automatic, I would say, in the operator world, because it's easy to preserve positivity in this. In this case, it's easy to preserve positivity of operators.
Yeah.
Under projections.
Yeah. Interesting.
Yeah. There are other similar. I mean, I didn't talk about this at all today, but like, for instance, if you're interested in representing generators, which are first-order differential operators of deterministic dynamics, like one of the fundamental algebraic properties is that they satisfy Leibniz rule. Like if I take the derivative of the product of two functions, we know how to do that. With there's a product rule for differentiation, and there is no non-trivial operator that satisfies that rule on finite dimensional spaces, commutative spaces. So if I take a function space and I discretize it somehow, I cannot satisfy the Leibniz rule. But on the other hand, it's very easy to satisfy the Leibniz rule with matrices. If you take, for instance, if I have a matrix A and I take the commutator between that matrix and any product of other matrices, if I look at the commutator of A and B times C, then it follows that this satisfies basically a Leibniz rule. So it's there are certain operations certain structures that are easier to represent in finite dimensions using spaces of operators than functions.
Cool, cool. Very interesting. Well, is there any other questions? Maybe.
Can I make just a couple of comments?
Mhm.
I mean, I think that there's two maybe two interesting differences between what's happening here and any other sort of dilation technique, which is that, you know, in addition to like coming up with this interesting mapping, you're also working with the quantum probability theory.
Mm.
And so you've like augmented your understanding of what the rules of probability do. There's potentially value in that. And, you know, so the second comment is specifically, if you were modeling the evolution of an actual quantum system, you would need to use those types of probability rules, like what you spoke about as like the quantum Bayes rule. That's essential for actually doing data-driven modeling of quantum systems.
Mm.
And there's like an enormous effort, you know, in trying to do that across the country at, you know, in almost every university. But I mean, right now we have Stephanie Filter, you know, sitting in the room.
Right.
She's working on ideas like that for modeling, you know, actual quantum hardware that people are building at the lab. And so you're augmenting your ability to do these data-driven systems, you know, not just in the representation, but in your notion of probability, which means the difference being you can form what are called these superposition states, where you can be in a combination of 0 and 1. Like Dimitrios didn't talk much about how qubits differ from classical bits, but you know they can have a probability anywhere between 0 and 1. In fact, they're like represent a two-dimensional manifold that's the surface of the sphere. So like you would never be able to work with that object naturally if you applied, you know, the standard rules of probability that almost all of these frameworks are built on, any kind of Bayesian analysis framework. And here you're actually augmenting your ability to deal with these quantum systems naturally. So there's some physical systems for which this will most certainly be a much more natural representation. I mean, that should be like an important, I know it's very abstract, but like there's like almost all fundamental systems obey quantum mechanics. And so that means there should be some evolution in the way we think about probability.
Yeah.
Yeah, I think that's a very good point, and maybe related to that, we haven't studied this at all, but like what might be interesting to think about is that once you go to this, you know, finite dimensional, again, representation, but then you're using quantum versions of, you know, probability and you know, Bayesian update. Is there anything to be said about having more capacity to encode information or make more, a better representation of your underlying, you know, unknown classical state for the same number of, for the same, you know, dimension, basically. You know, just because you're accessing all these, you're accessing potentially more states, you know, in your statistical representation of the unknown, you know, hidden state of your dynamical system. Maybe there are some benefits there. I don't know.
Well, I mean, you showed one at the very end, like where you know, basically you could interpret the theorem that he talked about at the end as saying there's an exponentially efficient representation for any integrable dynamical system. And what you're able to do then is to dynamically evolve an exponentially large number of states, essentially for the cost of, you know, a single or, you know, logarithmically smaller amount of information. Because you basically encode this in a set of qubits. So it's, I mean, it's you don't get something for nothing, but you do get a certain type of quantum advantage that is potentially very valuable. I mean, doing this for chaotic dynamics, which is more generic, it's not as easy.
No.
But like, you know, again, that's sort of cutting edge. Like, how would you do that? Anyway, I hope so. It's like some of these operations are actually, if you had a quantum computer, you could do them much more efficient. If that makes sense.
Mm.
Like exponentially more efficient, depending on what kinds of questions you're trying to ask.
Mm. Is Stephanie still there?
Am.
Oh, good. Well, I mean, I don't know. I'm guessing you are very inspired by Dimitri's talk. Maybe you can combine, you know, the neural ODE idea you're applying. Maybe you can apply that after some mapping, and then do the neural operator, neural ODE thingy. That sort of, you know, the combination. What do you think, Stephanie?
At this point, it's a little over my head, I have to admit.
Right,
But
right.
I'm curious. This is really the first time I see a talk like this. I think I'll have to digest and maybe discuss a little.
Yeah, maybe additional meeting with Stephanie would help. Sounds good. Oh, all right. Well, I'm in.
I think there was one more.
Yeah, I have
Go ahead.
just
Go ahead. Go ahead.
For example, in the first one is you have a scaling for its n square in your quantum implementation. Does it? But you have actually time evolution. Does it? This n square includes time evolution?
It's a good point. So this circuit, it's for one. At the moment, at least the way we have set it up, it's for one. This is giving you the evolution at the end of this for one fixed time. So that
one time step.
For orbit, it can be as long as you want it to be.
Because it's an integrable system,
Yeah.
you can fast forward it, so you can.
Okay, so it's sublinear time scaling. Right?
Exactly, because you know how to.
Yeah.
Usually, this is an interesting question. Like, what's the complexity of the evolution operation here? And it's a very interesting question from the point of view of quantum algorithms. You know, can you attain linear scaling in the time steps, or some algorithms have to do quadratic number of time steps, like quadratic work with number of time steps, which is weird compared to, you know, classical systems. But here, because it's integrable, you can essentially, you know, fast forward the videotape all the way to the final time step and immediately print the result.
At least fast forwarding is specific for quantum.
Specific for integrable systems.
For that have this pure point spectrum property.
And, yeah, actually, this n square it includes measurements, so you perform Fourier transformation and after that you just measure bit strings.
Yeah, and the reason that we do that is because one of the issues with quantum computing is that you cannot measure any quantum observable at the end. You have to measure. You're stuck with measuring a specific one associated with the quantum computational basis, so the qubits. So you want to rotate the state such that so when you do make that measurement, it actually gives you a correspondence with the underlying classical thing that you're trying to predict. And it turns out the quantum Fourier transform for the class of these multiplication operators that we use to represent our classical observables approximately diagonalizes them. So that means that you can, by doing the quantum Fourier transform, you rotate your state in a way that a quantum measurement can be encoded or decoded rather into an eigenvalue or a measurement of the multiplication operator that we care about.
So you kind of measure index in a spectrum and after that you convert.
Yeah, exactly.
Yeah, and the last question is about this forecasting data assimilation of measurement cycle. Maybe you can go to the slide because. Yeah. So basically, as understand, you need to perform this forecast and analysis for some J.
Yeah, J is the number of, sorry, I was going too fast here, the number of time steps between observations.
But after, if you would like to analyze another time step, you need to repeat everything probably.
Okay, so that's another good point. So here, you can think of it as an inference procedure, similarly to like Bayesian, like sequential Bayesian inference in classical statistics. Here, we're not doing any physical, quantum measurement. Yeah, that's a great point. That one of the challenges I think with implementing an algorithm like this, which is sequential in nature, is like, and you are actually doing real quantum measurements, that because those would destroy your state afterwards.
It just was, I was curious, but maybe you kind of, by doing measurements, you collapse your state. After that, you propagate maybe collapse state, not original state, but as I understand now, you just collapse, measure, and repeat it.
Yeah, well, right now we're not doing any physical measurements. So in other words, we don't have to explicitly like prepare the state. We can simply apply this rule to obtain a new density operator.
Okay.
I mean, I think extending it to the fully quantum case would be really interesting.
Yeah, and maybe there are something to be said here. There could be some role for quantum sensors, like in the sense of, yeah, like to be able to couple the quantum state with the whatever we get from the underlying system, whatever we observe from the underlying system, without destroying it. But I don't know if that's a.
I mean, I think, yeah, it depends on the level of description, but you could certainly destroy it, or I mean, you don't necessarily destroy it; you just project it.
Yeah. But then maybe the other issue is like when we do actually want to make a forecast, or like meaning to get a number out of it, right? Then we do have to destroy it in some sense.
Like project it along.
Actual state related to the time. If you project to something, you cannot continue your time evolution.
Well, I mean, it'll have a different evolution. I mean, it may have even the same Hamiltonian, just a different starting from, I mean, I think I would love to see people working this out. I think it's pretty valuable for dealing with the quantum information directly.
I mean that at the same moment before the measurement, you have some positional states that together describe time evolution. But if you collapse it, you will have just one initial time step, and basically you lose quantums without. You might lose quantums without.
Well, I mean, maybe you just projected an ancilla. Now you're. Okay, I think that's the final comment from the peanut gallery over here.
I don't know. I don't know. I was not monitoring the chat or anything like that. I couldn't see it. I hope there was.
No, there is no question from the chat. Yeah. Unless there is other questions from the audience. You can jump in. I see Lee here and also Ben here. You guys are welcome to jump in. Otherwise, from the perspective of formal DDPS seminar, maybe we can just end it and stop the record button and just continue the discussions. Well, in that spirit, let's thank our speaker Dimitrios for wonderful talk and nice Q&A sessions. Thank you so much.
Thank you. Thanks for coming.